それではレゲット教授による、特別講義をスタートさせていただきます。まず最初に私らの司会の前、物理学第一教室の前のです。よろしくお願いします。So good morning. This morning we have a great pleasure to invite Professor Anthony Leggett to tell us about an exciting story in the history of modern physics. He will tell us about how he solved the puzzles of the new phases of liquid helium-3 soon after their discovery in 1972. And his theoretical achievements, as you all know, led him to receive the Nobel Prize in Physics in 2003, 10 years ago, with Ginzburg and Abrikosov. And let me briefly introduce his bibliography, especially in his relationship with our department and the Yukawa Institute. He was born in London, or near London, in the London area, in 1938. And in his undergraduate years at Oxford University, he studied classics, that means Latin and Greek. And this probably and approximately means philosophy. And that is his undergraduate degree. But as a second major in undergraduate degree, which was very unusual at that time, even at Oxford, he took up physics. And then he went on to obtain doctor degree in physics at Oxford. And his advisor was Professor Telhart at Oxford. And the topic of his doctor thesis was on phonons in superfluid helium-4 and on the properties of dilute solutions of helium-4 in the background of normal phase helium-3. That was his PhD thesis. And he spent the period 1964-65 as a postdoc at the University of Illinois, Urbana, Champaign. And then, after that, he, for some reason, I don't know, he chose Kyodai, thankfully, and studied superconductivity. After studying his superfluid helium-4, he studied the superconductivity here in the group of Professor Takeo Matsubara, well known for Matsubara green function. And so he was a member of our physics department for 1 year. And this was in 1965, 1 year after Tokyo Olympics. And perhaps this was the time when our physics building was under construction. And he had his office in the Hitakan, the northern building, the older building, while the southern part was under construction at that time. And then he had a relationship with the Yukawa Institute. He helped to improve English written by Japanese physicists for the journal Progress of Theoretical Physics. And later he wrote a well-known note to Japanese scientists to how to improve their English, and where he introduced the viewpoint known as Leggett's tree, and to compare English and Japanese way of explaining things. Then since 1967, he took the position at the University of Sussex, and since 1983, he has been a professor at the University of Illinois, Urbana, Champaign. And besides his work on superconductivity and superfluidity, of course, and superconductivity, including high-temperature superconductivity, he is also very well known for setting directions for research in quantum physics of macroscopic dissipative systems and use of condensed matter systems such as Josephson junctions to test the foundation of quantum mechanics. And he is also well known for his study of low temperature properties of glasses. And he is also active in the study of Bose-Einstein condensation of atomic gases. In the last 3 years, he has been invited to stay for 1 month every year at Todai on this JSPS program. So this year he will give a series of lectures at Todai on topological quantum computation. Then, so since, and also he's one of the international advisors of the Shingakujitsu project, a new national research project on topological quantum phenomena. This is represented by the logo given here. Topological quantum phenomena is an international advisor. So we take these opportunities to ask him to come to Kyodai at this time. So this lecture is also supported by Yukawa Institute. So this morning he will tell us about the story of solving the puzzles of superfluid helium-3, more specifically the NMR puzzles of superfluid helium-3. So please welcome Professor Leggett.
Thank you very much. As Professor Maino has mentioned, I spent a very happy year here at Kyodai in 1965, and it is a great pleasure to be back here today. I'm going to tell you essentially the same story as I told in Stockholm on the occasion of the award of the 2003 Nobel Prize. So let me start by just introducing superfluid helium-3. Helium, as you know, comes in two varieties, that is, two different isotopes. And since very many years, essentially since certainly since 1938, it has been known that the heavy isotope, the common isotope, helium-4, becomes superfluid below 2 degrees absolute. When we say it becomes superfluid, we mean, crudely, that it flows through small pores without apparent friction and displays many other intriguing phenomena. Now, liquid helium-3 has only been produced since about 1950. It has been produced primarily by the decay of tritium in nuclear reactors. So it's only been around for a few less years than helium-4. However, there's a system which we believe is very similar to helium-3, which has been around for a very long time, namely the electrons in metals. The main and most obvious difference between the electrons in metals and helium-3 is that electrons in metals are charged, whereas the atoms of liquid helium-3 are electrically neutral. However, these two systems have in common that they both consist of particles of spin 1/2. Therefore, we believe that such particles must obey Fermi statistics. So, what does that imply? Well, basically, if we imagine such a system at low temperatures, and we plot the number of particles per quantum state as a function of the energy of the state, it's pretty boring. Most of the particles are confined in the so-called Fermi sea. That is, they simply have one particle per state, and there's not much we can do with that. The Fermi sea is rather inert and unexciting. The only excitement, if any, takes place near the Fermi surface, And for a non-interacting gas, of fermions, particles obeying Fermi statistics, near the Fermi surface, Fermi energy, the curve falls off like this, with a width of approximately the thermal energy kT. So it's only this small shell of energies close to the Fermi surface which are in any way interesting for a low temperature system of fermions. So this is the picture we have for a non-interacting gas. In a very important piece of work in 1957, Landau showed that interactions don't change the picture qualitatively, at least in the so-called normal phase. Instead of a degenerate Fermi gas, we have a degenerate Fermi liquid. But qualitatively, nothing much is changed. Now, for many years, more than 100 years, we have known that the electrons in metals, which have a Fermi temperature of about 10 to the 4 to 10 to the 5 degrees Kelvin, sometimes these electrons undergo, below about 20 degrees, the phenomenon known as superconductivity. And as you know, superconductivity is essentially superfluidity occurring in a charged system. So although it looks at first sight very different, it's basically, we believe, basically superconductivity and superfluidity are essentially the same phenomenon. Now, in the case of helium-3, the Fermi temperature is only about 5 K compared to 10 to the 4, 10 to the 5 here. But scaling the temperatures appropriately, we might guess that possibly at temperature below, let us say, 10 to the minus 3 K, 1 millidegree, at such temperatures, the atoms of helium-3 might undergo a similar transition to the electrons in metals. However, since they are not charged, they would not strictly show superconductivity, but rather superfluidity, rather like in helium-4. And this idea was actually developed quite early on in the late 50s, as we'll see. Going back for a moment to superconductivity, there were two very brilliant theories of superconductivity in the 50s. First of all, there was a brilliant phenomenological theory due to Ginzburg, Abrikosov, and other people in the years 1950 to 1955. And basically, they introduced the idea of a macroscopic wave function. At the time, I think they didn't really quite know what that was, but it was a very brilliant piece of phenomenology, and they were able to explain many of the important properties, the macroscopic properties of superconductors using this idea. A few years later, my former colleagues, Bardeen, Cooper, and Schrieffer at the University of Illinois produced a microscopic theory of superconductivity. And, as you know, nowadays we believe that at least for what we call the old-fashioned superconductors, that is, crudely speaking, the ones known before about 1975, this is essentially the correct theory, so we believe. And what Bardeen and company proposed was that the electrons in a narrow energy shell of a width something like Boltzmann's constant times the transition temperature, which is 20 K or so, the electrons in this narrow shell form what are nowadays called Cooper pairs. So you can think of Cooper pairs as rather like a sort of giant diatomic, more precisely dielectronic molecule. So you have an electron here and an electron here, and they are forming a Cooper pair. However, what you have to realize is that the size of this Cooper pair is very large compared to the distance between electrons. So between these two electrons, which are forming a Cooper pair, there are millions of other electrons which are all doing their own correlations. It's a very highly correlated system. Now, sometimes people compare this to certain kinds of modern dance, in which my motion may be correlated with that of my partner, but she is way across the room, and between us there are any number of other couples who are all forming their own correlations. It's a very highly coherent and correlated phenomenon. Typically, the radius of a Cooper pair in a metal like aluminum might be, say, 10 to the 4 angstroms. Now, a very crucial feature of the formation of Cooper pair, of BCS theory, which is one I'm going to be repeatedly exploiting in this lecture, is that all the Cooper pairs, once they're formed, must behave in exactly the same way. A very crucial feature. And in fact, it turns out that the macroscopic wave function of Ginzburg and Landau is simply the common centre of mass wave function of all the pairs. As I said, they must all behave in the same way. And so the macroscopic really refers to the fact that this wave function is common to a macroscopic number of Cooper pairs. Now, in the original BCS theory of superconductivity, one has a centre of mass wave function. One also has an internal wave function. That is, you have to ask, what is the internal structure of these pairs? So it's like asking, what is the internal wave function of a diatomic molecule? And in the case of the original BCS theory, the answer is it's actually very boring. The internal wave function simply consists of a spin singlet wave function. So the electrons are all, the pairs, the spins are all opposite. So you have 0 total spin. And moreover, that's multiplied by a spherically symmetric, or L equals 0, orbital wave function. So that means that the pair looks the same from any direction, basically. So more technically, in the original BCS theory, there are no internal or orientational degrees of freedom. So from that point of view, the original BCS theory, as I say, is very boring, although of course it's extremely interesting from many other points of view. However, very soon after the original BCS theory, people started thinking about the possibility of a similar phenomenon, Cooper pairing, taking place in liquid helium-3. However, they soon realized a very important difference between the two cases, apart from the fact, of course, that the helium-3 atoms are neutral, which we've already said. The electrons in metals have a Coulomb repulsion, of course, but at short distances, that only goes as 1 over r, which is not particularly strong, so a particularly strong repulsion. By contrast, in the case of two helium-3 atoms, because of the effects of the Pauli principle and other things, they have a very strong hardcore repulsion. But basically, it's impossible for two helium-3 atoms to approach one another closer than about 2.5 angstroms. However, at slightly larger distances, there is an appreciable attraction due to the van der Waals interaction. That falls off as the inverse 6th power, and they go to infinity. Now, if the Cooper pairs are going to form, it presumably has to be because they enjoy some kind of attraction. And that means they must have an appreciable probability of being able to get within this kind of distance of one another. So in other words, you must have R, you must be able to get R of the order of R0. On the other hand, the momentum, since these Cooper pairs are formed out of a shell very close to the Fermi surface, the momentum must be close to the Fermi momentum, given by this expression here. So if we take these together, that means that the relative angular momentum, which is simply Pf times, P times R0 in units of h bar, that we would expect to be non-zero. And the general expectation in the early years was that it was probably 2, but possibly 1. Well, now, this has an interesting consequence. According to the Pauli principle, if I have two identical fermions, then if the orbital, relative orbital angular momentum, L, is even, then in order to respect the Pauli principle, the spin, total spin, must be 0. In other words, I must have a singlet, spin singlet state. On the other hand, if L is odd, 1 through 5, then I expect total spin 1, that is a triplet state. But in both cases, the fact that L is not equal to 0 means that the relative or internal wave function of the pair must have non-trivial orientational degrees of freedom. And people very early on realized that that made the Cooper pairs in, if indeed there were some, in helium-3, they would be more interesting from this point of view than the Cooper pairs in a BCS superconductor. So as I say, it's a long history there, starting in the late 50s. In a very important paper in 1961, Anderson and Morel explored in detail the possibility that for helium-3, L would be equal to 2. They also, much more briefly, explored the case of L equals 1. And in that case, they only studied one particular possibility, namely the possibility that the Cooper pairs form either 2 upspins or 2 downspins, and those upspins and downspins have the same orbital angular momentum. This and also this. So the angular momentum is the same for the 2 groups of spins. This is nowadays, for reasons we'll see, called the Anderson-Brennan-Morel state, such a state. In such a state, the physical properties should be anisotropic because the angular momentum now picks out a particular direction. A couple of years later, independently, Dovin in the former Soviet Union and Balian and Wertheimer in the West realized that the kind of case which Anderson and Morel had considered was not the most general. In fact, in the case of L equals 1, all the spin components, the possible spin components, can form. In other words, you need not have just up and down. Instead, you can have this symmetric combination of up, down, plus down, up. That still has total spin 1, so it still obeys the Pauli principle. And in fact, you can form a particular state in which the orbital angular momentum is exactly, of your Cooper pair, is exactly opposite to the spin. In other words, in the language of molecular physics, total J is 0, you have a so-called 3p0 state. Nowadays, this is, since the work of Dovin was not known in the West for many years, this is usually called the Balian-Wertheimer state. Interestingly, for a state of this form, or exactly this form, all the physical properties are isotropic. This basically is a consequence of the so-called Wigner-Eckart theorem, which tells you that, that any characteristic vector of a quantum state can only be proportional to the total angular momentum. In this case, the total angular momentum is 0. So there can be no characteristic vectors, everything must be isotropic. An interesting further consequence, which Dovin and Balian and Wertheimer drew, was that this state here, is more stable than any so-called equal spin pairing. Equal spin pairing refers to the case only up, and down. But what they showed was that that was unstable with respect to any to this baryon-Wertheimer state. So, when I first started thinking about, I basically started getting interested in the possibility of superfluidity in helium-3 in 1964, when I was a postdoc with David Pines at the University of Illinois in Urbana, Champaign. And I continued that interest during my year here at Kyoto in the group of Professor Takeo Matsubara in 1965. And at that time, the theoretical expectations were roughly like this: that liquid helium-3 may form Cooper pairs, either with even orbital angular momentum, in which case we got a spin singlet, or with odd angular momentum, in which case it was predicted that we got the baryon-Wertheimer state. Now, in either of these cases, the spin susceptibility would be reduced. Why? Well, both in the case of spin singlet and also in the case of baryon-Wertheimer, you get some spins formed oppositely. Those pairs cannot respond to an external magnetic field. So that means that by comparison with the normal state, the spin susceptibility would be reduced. However, all the magnetic properties would be isotropic. What about the transition temperature? Well, that was always the most difficult thing to predict. What happened during the 50s and 60s was that theorists kept predicting a transition temperature to superfluidity which was just a little below where the experimentalists had actually got to. Then the experimentalists would improve their technique, go down to slightly colder, and not find anything, and of course the theorists would then revise their calculations, always keeping just that little bit ahead. However, I think I'm correct in saying that in the early 70s, in 1971 or thereabouts, there was at least one paper, I think in the former Soviet Union, which decided, a theoretical paper, which decided to really play it safe. So they went through a long argument. It was connected with an old argument of Kohn and Luttinger, and they came out eventually with a value of transition temperature which was 10 to the minus 17 degrees Kelvin, which was really well beyond the reach of the experimentalists at that time. Well, as I say, that's how things stood in the late 60s. In June of 1972, well, let me start off with something a little earlier. In the late fall of 1971, Doug Osheroff, who was at that time a graduate student of David Lee in Cornell, he was doing experiments on using so-called Pomeranchuk cooling, which meant that he was trying to pressurize a mixture of liquid and solid helium-3. So the only thing they could really vary was the temperature, and Doug was looking at the pressure as a function of temperature, and therefore as a function of time. And sitting there in the lab late one night in November of 1971, he saw two very small anomalies in the pressure versus time curve. Initially, this was interpreted as evidence for a magnetic phase transition in solid helium-3. And in fact, when the Cornell group published the results of this experiment in early 1972, the title of their paper was indeed Evidence for a New Phase of Solid Helium-3. So that, however, later experiments, which I'll come to in a moment, showed quite unambiguously that whatever was going on in the liquid, not the solid. And with hindsight, we can see that what Doug Osheroff had found was two phase transitions in the liquid. The first It's second order and occurs at about 2.65 millikelvin. Nowadays we call that T sub A. The second, first order, occurred at about 2.0 millikelvin. So the inference following this was that we have now three phases of helium-3, of liquid helium-3 at low temperatures. You have the normal phase, above 2.65 K, the A phase, which exists between 2.65 and 2.0 K, and finally the B phase, which exists at low temperatures. Well, so far so good, but there's something in some sense much more intriguing which came out. The second round of experiments, which were the ones which actually showed unambiguously that odd things were going on in the liquid, these were actually Nmr experiments. Okay, so how does a typical Nmr experiment work? Well, you have a static external field, let's say in the z direction, and you apply an oscillating RF field perpendicular to it, and you vary you can vary either the frequency of the field or the magnitude of the absorption of this external field here. What you basically plot, let's assume, it isn't historically quite right, but let's assume you vary the frequency. So you measure the absorption as a function of the frequency. And by integrating the absorption, you can get out the static spin susceptibility. Now, in the end state, in the normal state, the spin susceptibility turns out to be independent of temperature, and its value is just as expected for a degenerate Fermi liquid. So no big surprise there. Again, the absorption shows a very sharp peak as a function of frequency at the so-called free atom normal resonance frequency, which is simply gamma, the gyromagnetic ratio of the free helium-3 atom, which is about 3,000 first per Gauss, times the external field. And they could they checked that this quality was very accurately fulfilled in their experiment. So far, nothing at all unusual. All this is telling you, really, is that the total magnetic field, which the helium-3 nuclei are seeing, is simply the external field, as one would expect. So nothing at all unusual in the normal phase. Now things got a lot more interesting when we come to the A phase. Oh, sorry. Okay, so when we come to the A phase, the susceptibility apparently remains constant. Nothing much changes there. When we come to the B transition, however, the susceptibility drops discontinuously and then continues to go down. Well, by itself, that's not necessarily very mysterious. The A phase, for example, could be a so-called ESP phase, only up and down pairs. In that case, there would be no reduction in the susceptibility. The B phase could be either a spin singlet or the Balayan-Wertheim phase. In that case, you'd have some up-down pairs formed, so chi is indeed reduced. The only problem with this conjecture is that you remember that the ESP phase should not be stable with respect to the Balayan-Wertheim phase. But that was really the only thing that goes wrong, as it were, with the susceptibility. However, the resonance frequency is much more intriguing. So in the normal phase, it's constant. It's simply equal to gamma, gyromagnetic ratio, times the external field. Nothing mysterious at all. As we go into the A phase, the resonance stays very sharp. However, its frequency starts to shift up away from the normal frequency. And what is particularly interesting is that by varying the external field, the Cornell group found that the shift was not simply proportional to the shift in external field, rather it obeyed a so-called Pythagorean relation. That is, the square of the resonance frequency was the sum of the original normal frequency squared plus some additional term here, which appeared to be a function only of temperature. And in fact, they found that as a function of temperature, it was given approximately by this formula here. And the value of the A, which occurs here, is something like 5 times 10 to the 10th hertz squared. So, this is what Bob Richardson told me when he visited Sussex in, I think, early June of 1972. And I started thinking about this. This seemed extremely puzzling. The most obvious explanation, of course, of a Pythagorean relation like this is that somehow in the A phase, oh, incidentally, let me just make one more remark. The A phase can be supercooled across this transition. That is, you can actually cool somewhat below this transition without getting the B phase. And if you do, then the resonance frequency continues to go up and down. However, as soon as you make the transition to the B phase, the resonance frequency appears to drop back to the same value as it had in the normal phase. Okay, so as I say, the most obvious explanation of what's going on in the A phase is that in this phase, somehow there was developed an internal field which is orthogonal, that is perpendicular to the external field. And then you add these two together according to Pythagoras' theorem, and what you find is that the magnitude of the total field, of course, is given by the usual formula, the square root of the sum of the squares, and that would, and if your resonance frequency that was then appropriate to this field, you would get this relation. Only problem, where is that field coming from? It needs to be quite large if you look at things this way. You need a field of the order of 30 Gauss. However, the electrons in liquid helium are totally inert. I mean, the excitation energy of the first electronic excited state is something like, I think, 40 electron volts. It's enormous. So almost certainly the electrons can't be contributed. So the only thing that's left is the very tiny magnetic field due to the nuclear dipoles themselves. That is, the only spin non-conserving force in your problem is the nuclear dipole-dipole interaction. And now you do a calculation. You try to pack your helium-3 atoms as close as you can possibly pack them, and you ask, what is the magnitude of the dipole field? And the answer is it's less than 1 Gauss. So you're certainly not going to be able to get out anything like 30 Gauss. And actually, there's all sorts of other reasons why this picture is not at all plausible. And when I first realised this, I was really shocked. I had been, at that time, intending, I'd made a rather firm decision to myself that I would stop doing low-temperature physics and go off and spend all my time on the foundations of quantum mechanics. However, these results seemed to me so extraordinary that I seriously began to wonder whether this is the first indication of a radical breakdown of quantum mechanics. You see, it wasn't all that implausible. After all, I was taking a very dense system, very dense, very strongly interacting, down to a temperature where no one had essentially taken it before. Who knows whether the standard laws of quantum mechanics or statistical mechanics might not fail under those conditions. So this seemed a really very exciting prospect, and I decided to drop my intention to go into the foundations of quantum mechanics for a bit until I'd verified whether or not quantum mechanics was still working under these conditions. Well, there aren't very many things, there aren't very many results that one can prove exactly in condensed matter physics. And many of the things that you can prove exactly are a consequence of so-called sum rules. So my first thought was to see what I could get out of sum rules applied to this situation. And I won't go through the details, but it turns out that if you apply standard sum rule arguments to the nuclear magnetic resonance in helium-3, in liquid helium-3, you find that if a single sharp resonance is absorbed with a frequency only the sine resonance, as it was in the experiment, then in fact its frequency should be given by the original Larmor frequency squared plus a term omega 0 squared. In other words, we should get a Pythagorean relation, as was seen in the experiments. Now, what about the value of omega 0 squared? Well, omega 0 squared has to come, as I said, from the nuclear dipole-dipole forces. And one can show that its value is given by the original gamma squared, the diamagnetic ratio, times the inverse of chi, times the second derivative of the nuclear dipole energy when you rotate the spins, leaving the orbital coordinates fixed. However, this second derivative, from rather general arguments, is of the same order as the dipole energy itself. So, putting that in here, we find that the experimental value of omega 0 squared root t is given by a formula of this type. So it is, encouragingly, it's proportional to the deviation from the A temperature as seen in the experiment, but this factor k would have to be something like 10 to the minus 3 ergs per centimeter. Now, that doesn't sound a lot. And in fact, if you work out the maximum total dipole energy, that nuclear dipole energy which you could conceivably get in your system, it would in fact be a lot larger than that. However, there's a very serious objection. Suppose that I've got two spins, two nuclear spins, which are sitting at given position relative to one another. Then, as you know, the spins behave like small magnets. Now, if you've ever played around with magnets in the laboratory, you know that if the magnets are parallel, then they would much rather sit end to end than side by side. In fact, if you try to put them side by side, they'll rapidly readjust themselves so as to go end to end. You know, if you say it's a very common experience in the laboratory. So in other words, this side by side configuration is bad, whereas the end to end configuration is good. However, here comes the crux of the matter. What is the difference in energy between these two configurations? Answer, it's this order of magnitude where mu n is the nuclear magnetic moment, R0 is the distance of closest approach. That's of the order of 10 to the minus 7k, which is 4 orders of magnitude smaller than the temperatures we're thinking about. So what that will mean is that at first sight at least, the overall preference for the good orientation over bad is at most something like this ratio here, delta E over kVt, which is the order of 10 to the minus 4. In other words, any attempt to realize the good configuration all the time will rapidly be defeated by thermal fluctuations. Okay? In other words, and once you've got that result, the expectation value of dipole energy turns out to be much, much smaller than the value you need. So this was the dilemma. And this really, really intrigued me. And I really started lying in bed at night thinking about how this could possibly happen. And eventually I did come up with a possible answer to how this could be. It goes something like this. I think it's an idea which I called rather clumsily spontaneously broken spin orbit symmetry, SPSOS. And I think it's most easily understood by analogy with the behavior of a ferromagnet. Now, in a typical ferromagnet, like iron, say, the Hamiltonian contains one term, H0, which is just the usual exchange effects and so forth, kinetic energy, whatever, exchange effects. This part of the Hamiltonian is invariant under simultaneous rotation of all the spins. However, you also have the Zeeman term in the Hamiltonian, which is not invariant under rotation. It breaks the spin rotation symmetry. And, of course, the Zeeman energy is proportional to the external field. Now, if we take iron, say, then in the paramagnetic phase above the Curie temperature, the spins are all basically behaving independently. In other words, the thermal energy is competing with the single spin Zeeman energy here. That means that the typical polarization of the spin is of the order of the ratio of the Zeeman energy to the thermal energy, and typically that's much less than 1. So when you now evaluate the expectation value of the Zeeman energy, it comes out proportional to n times h squared over kT, which in some sense is a rather small quantity. On the other hand, if I go down to the ferromagnetic phase, now we have the following situation. The H0 terms in the Hamiltonian, that is the kinetic energy, the exchange energy, and so on and so forth, that forces all the spins to lie parallel. It does not tell you in which direction they have to lie. This is where the Zeeman term comes in. So, crudely speaking, what one must now do is to compare the situation where all the spins are pointing upwards along the field with the situation where they're all pointing downwards. Remember, they have to all lie parallel in the ferromagnetic phase. So it's either this or this. Now, the difference in energy is not the single spin Zeeman energy, but n times that. And that's what the thermal energy is now competing with. And therefore, in fact, because of this number is huge, something like 10 to the 23, this is much larger than this, which means that essentially the system behaves so that all the spins are forced to lie parallel to the external field. That in turn means the expectation value of the energy is now simply Nmr rather than this much smaller quantity here. Now let's try to look at the analogy for liquid helium-3. In helium-3, we have a large term in the Hamiltonian. That's the kinetic energy, the van der Waals energy, the exchange energy, other things. And that is invariant under relative rotation of the spin and orbital coordinate systems. However, there is this tiny term, the nuclear dipole term, h sub d, in the Hamiltonian, which is not invariant. It does matter what is the orientation of the spins relative to the orbital coordinates. In other words, this is indeed better than this, and so on. In other words, the dipole energy breaks the relative spin-orbit rotation symmetry. Now, in the normal phase, there's nothing to say that all the pairs of spins have to correlate the behavior. So they all behave independently. So the argument I gave previously basically works. The polarization is of the order of GD, the dipole coupling constant, divided by KT, much less than 1. So the dipole energy is proportional to n times GD squared over KT. You have to remember, G sub D is a tiny, tiny quantity. So its square is even tinier, and although you would expect a very tiny shift in the normal phase, it certainly would not have been seen in the experiments in the 1970s. Interestingly, actually, in more recent years, people have just barely been able to observe this tiny shift, but it really is extremely tiny. However, now suppose we go into the ordered phase below T sub O. Then the H0 would again force all the pairs. Okay, this is a conjecture. That we have a sort of collective transition in which H sub 0 forces all the pairs to behave similarly, but does not tell them which way they should behave. So that means that KT is now competing not with the single pair coupling constant, G sub D, but rather with n times that. Again, because of this huge number n, about 10 to the 23, this one is much larger than this. That means that the good orientation unambiguously wins out over the bad orientation. In other words, all the pairs now prefer to lie like this, end to end, rather than like this, side to side. As a result, just as in the ferromagnetic case, the expectation value of the dipole energy is now not proportional to GD squared, but to GD. And lo and behold, if you work out the actual numerical value, it comes out to just about 10 to the minus 3 ergs per centimetre cubed, which is exactly what we needed to get agreement with the experiment. So this made me very excited. And I wrote a draft manuscript and got my colleague Mike Richards to present it at the upcoming low temperature conference in the US in the late summer of 1972. Now, I went a little further than that. I introduced this idea of spontaneously broken spin-orbit symmetry as a rather general idea, but then, of course, one has to ask, well, you know, how could it happen that H sub 0 would force all pairs to behave similarly? Well, it could have been because of some kind of, say, ferromagnetic kind of transition, but the most probable, most plausible explanation did seem to be the kind of Cooper pairing transition which people had already postulated. So I was able to show that if the A phase of helium-3 was indeed the postulated Cooper paired phase, and it had to be basically an equal spin pairing phase, then indeed this would work, and I'd get roughly this number. Because I still had to explain why the B phase did not show an NMR shift. And in my original letter, I said, well, since it doesn't show an NMR shift, presumably it's not a spin triplet Cooper paired phase, so that leaves basically two possibilities. It could either be a spin singlet phase, or it could be some completely unknown kind of phase which had nothing to do with Cooper pairing. But I basically left it at that. Well, before I go on, let me just illustrate the fact that the idea of SBSOS, spontaneously broken spin-orbit symmetry, is actually, I think, a little more subtle than that of ferromagnetism. And to do that, let me go to this slide. In a ferromagnet, we basically have only one kind of angular momentum, namely the spin. And you have a rather simple situation. In the paramagnetic phase, all the spins, the normal phase, all these spins are completely disordered. In the paramagnetic phase, the ordered phase, they're all lying parallel. Okay, no big surprise. The expectation value of the total spin, of course, is non-zero. It's zero in this phase, non-zero in this phase. Liquid helium-3, the situation is a little more complicated. It may be, and this actually turns out, as we'll see later, this turns out to be the case for the B phase. You might have the following situation. In the normal phase, you see that there are two types of angular momentum. Red is the total spin, green is the total relative orbital angular momentum. And you see that in the normal phase, the green arrows are completely disordered. The red arrows, similarly, are completely disordered. And moreover, there's no particular relation between the red and green arrows. Now look at the ordered phase. Now you see that the red arrows by themselves are completely disordered. The green arrows, similarly, by themselves are completely disordered. However, there's always a definite ordering of the green arrow with respect to the red. That's always the same, it would expect. And what that means formally is that while the total spin is zero and the total orbital angular momentum is zero, there does exist a vector which is L cross S, the vector product of L and S, which is non-zero in this phase. That's really quite a subtle point, which we'll come back to at the end of this lecture. Okay, well, for the next few months, I was pretty much busy teaching at Sussex. I had a fairly heavy teaching load, and so I wasn't able to do a great deal more on the experiments in helium-3. In the meantime, however, there was a very interesting development with which I was not associated, but it's well worth reviewing nevertheless. And this was due to Anderson and Brinkman. You remember that in BCS, we covered in theory, for the L equals 1 case, the Balayan-Wertheim phase is always stable, independently of pressure and temperature. And this did not seem to be an agreement with experiments, because it looked as if there was increasing evidence that the A phase was indeed a so-called equal spin pairing phase, not the BW phase. The B phase, as we'll see, could be the BW phase. We'll come back to that point later. But the A phase certainly was not. What Anderson and Brinkman did was to point out a crucial difference between Cooper pairing in superconductors and in helium-3. In superconductors, according to the BCS theory, two electrons of opposite spin and opposite momentum interact by exchanging a lattice vibration, a phonon. Now, the crucial point is that that phonon is very insensitive to the onset of superconductivity. It's very, very difficult, it's just possible these days, but very difficult to see any effect of superconductivity on the phonon spectrum as measured, say, in neutral scattering. So, this is a big, however, they pointed out that when you put helium-3, things are really rather different. Already it had been speculated, way ahead of the experiments, that an important mechanism of pairing in helium-3 was the exchange, not of phonons, but rather of spin fluctuations. So this idea was, I think, well, was due to a number of people, particularly Laser and Fay, and it had been explored quite a bit before the experiments. Now, the crucial difference is that the spin fluctuations are fluctuations of the helium-3 system itself. Remember here, what you're exchanging, the phonon, is a vibration of the ions, which have nothing directly to do with the electrons. Here, it's actually the helium-3 itself which is giving rise to the spin fluctuations, and therefore you might expect that these spin fluctuations would be sensitive to the onset of pairing. In other words, you get a sort of feedback effect. The onset of superfluidity, of Cooper pairing, affects the mechanism which originally gave rise to that pairing. Now, when they started to explore the consequences in more detail, Anderson and Brinkman found a very fascinating result. They found that over most of the phase diagram, the BW state would indeed be stable, just as in BCS theory. And that was very nice, because by this time it had become obvious that, in fact, the B phase was stable over most of the phase diagram. It's only a little wedge, the A phase was stable. That was at high temperature and pressure. There they found that feedback effects not only favoured an unequal spin pairing state, miraculously, it uniquely favoured the original ABM phase. That was actually quite surprising, because remember that, in some sense, when Anderson and Morel had done their work in 1961, they'd chosen arbitrarily, apparently arbitrarily, to consider only a state in which you had up and down form, and they had the same angular momentum. That's not by any means the only possibility. For some reason, they just happened to discuss that particular state. Now it kind of turns out it's exactly that state which is favoured. I've often wondered whether they had any reason to pick that state, and I think the answer is no. It's just right. Anyway, it does favour that. And because of this work of Brinkman, it's now called Anderson-Brinkman-Morel. So yeah. Now I want to emphasise, this is really a major qualitative leap beyond BCS theory, and it's a consideration which has led to, I think, some interesting considerations more recently regarding the high temperature superconductors and so forth. Anyway, going back to my own involvement in this business, during the 8 months or so following the summer of 1972, when I was, as I say, I was myself mostly occupied in teaching, I didn't have a lot of time to devote to it, my colleague Mike Moore kept on nagging me, and he said, all these sum rule arguments are all very well, but they don't add up to a microscopic theory. You've really got to try to construct a decent microscopic theory of what is going on in this electromagnetic resonance. And by that time, already some theories floating around, which, for one reason or another, didn't always seem to work, so it seemed a challenge. And in April of 1973, I was invited by Bob Richardson, the leader of the experimental group at Cornell, to spend a month at Cornell and interact with them on these new experiments. And I have to say, I think that was probably the most exciting month of my life in terms of research. I was basically, I was by myself. I could afford to spend 16 hours a day just thinking about these things. I was going down all the time to the basement, to the experimental labs, to talk to the people there, and gradually trying to develop a microscopic theory. Eventually, I did so at roughly this is how it works. The basic variables of your theory are the total spin S and something which is subtly different, it's the orientation of the spin of the Cooper pairs. That is, you imagine you start from some kind of reference orientation, and then you ask, how is that being rotated? And it turns out that, first of all, that these two variables actually satisfy a rather nice commutation relation here. And thereby, incidentally, there's a sort of sum plot, which I should just mention, since it is connected with the work I did here in Kyoto in '65. When I came here to work in Professor Matsubara's group in the fall of '65, I didn't really have a clear problem to work on. And so I started looking at the recent literature. And there was a paper, an experimental paper on niobium, which claimed that they had evidence that niobium was a so-called two-band superconductor. That is, it was a superconductor in which two different energy bands intersected the Fermi surface. Now, there's been a little work on that, but I thought this was interesting and worth studying. And so I began to wonder whether there might be a sort of internal Josephson effect between these two bands. And so I started to try to work that out, and I did work out some kind of theory. And during my year here in Kyoto, I actually sent off a couple of papers actually to Progress of Theoretical Physics, and eventually they got published. Well, unfortunately, no sooner had I sent off my papers to the journal when there was a new set of experiments which showed that the old ones were wrong and that niobium was not a two-band superconductor after all. However, I'd done the work, it was there, written down and so forth, and when I came to look at this problem of helium-3, it was precisely that which guided me eventually to this formulation. So I say that because there's a moral there. If you've done a decent and careful piece of work, don't ever think it's been wasted. It never has. Even if it seems at the time to have been wasted, well, just put it away in a drawer, write it up carefully, put it away in a drawer. I would bet that 15 or 20 years down the road, it'll come back and help you out, as it did in my case. Anyway, so we have this nice commutation relation here, and then we have a Hamiltonian. Now this was, I think, an interesting piece of physics in the argument. I argued that the time scales involving these two variables, which are essentially macroscopic variables, time scales were long enough. They're much longer than any characteristic microscopic time, like, for example, that associated with the energy gap or that associated with quasi-particle relaxation and so forth. And therefore, you could basically take a Born-Oppenheimer approach and write an effective Hamiltonian in terms of these two slow variables. These two slow variables are rather like the variables describing the nuclear motion in a diatomic molecule. You remember that in the Born-Oppenheimer approximation, what you do is to study the behavior of the electrons for fixed nuclear positions, and only after that you worry about nuclear motion. We basically were doing the same. We're asking what is the equilibrium state of the system for fixed S and fixed theta, and then later we'll come back and worry about the motion of these. Anyway, given this, you can write down a couple of semi-classical equations, actually. The motion of the orientation, theta, is the Cooper pair orientation is given by this formula, which gives you H external minus chi to minus 1s. And the nice thing about that is that you see that in thermal equilibrium, when S is equal to chi times H external, this is 0. So as you'd expect. In other words, the Cooper pair orientation is fixed in equilibrium. As to the motion of the spin, you have the normal long precession term in the external field. Then you have this dipole torque term. And the interesting thing about this is that it cannot, in general, be written as simply S cross some field. So you remember this original argument about how you got the Pythagorean formula by having two fields which were mutually perpendicular. That turns out to be totally misleading. You just can't write the theory in that kind of form. So in fact, so this then involves the properties of the Cooper pairs. And it turns out, if you just linearize these equations, that the linear NMR behavior is completely determined by the eigenvalues of this quantity here, the second derivative of the dipole energy with respect to the orientation of the Cooper pairs. Now I think that's a rather very satisfying result, is what it means is that since we can work out that any proposed Cooper pair state and work out precisely how this quantity behaves, we can then compare that with the experimentally observed behaviour. In other words, we can fingerprint the A and B phases by the NMR. So when we take it a little further, it turns out the ABM phase shows a single resonance line, which was indeed consistent with the experiments. The axial phase, the so-called axial phase, I should just describe what that is. It means a state which is like the ABM phase, but now the up spins have one angular momentum, the downs have the opposite angular momentum. Okay? So they're actually a different phase, and it has different values in this quantity, and as a result you get a split resonance. Now the interesting thing was that by the time I did this work, Anderson and Brinkman had already shown my other things that the axial phase would never be stable. It would always be unstable either with respect to ABM or BW, or both. Nevertheless, it did seem worthwhile checking. So in fact, the Cornell group did start experiments rather soon thereafter to check whether the resonance was split or not. However, the BW phase is really interesting. Remember the original BW phase, which they wrote down, had L opposite races, in other words, J equals 0. However, the dipole torque, is what that's going to do is to rotate S relative to L by an angle which is the inverse cosine of one supporter, that's 104 degrees. And around some axis, omega, and it turns out the best choice of the axis omega is the axis of the external field. Now that's very interesting, because what does that mean? Now you have to do a little geometry in your head, if you can. In transverse resonance experiment, you've already got a large rotation around this fixed axis, the axis of the external field. You go to a small transverse field, that's not going to change the angle to the first approximation. All it's going to do is to make a small shift in the axis of the rotation. But since this quantity here depends only on the angle and not on the axis, that means that the resonance is unshifted, as indeed it is in the experiment. So the fact that remember that the resonance frequency went up in the A phase and then fell down, that has a simple explanation in these terms. However, here's the really nice thing. Suppose that I do an unusual type of Nmr experiment where I polarize my RF field along the external field. Now you see that corresponds to rotating the Cooper pairs further away from 104 degrees. That does give you a non-zero restoring torque, and you expect to get a finite frequency longitudinal resonance. So that were the predictions of the microscopic theory that I evolved in April of 1973. So don't seem to be going any further. Okay, I'll have a couple more slides, I think. Okay, good, fine. This is my last slide. Okay. By the summer of 1973, one could already conclude that both the a priori stability considerations, the sort of thing that Anderson and Brinkman had done, and the NMR experimental data, both were consistent with the hypothesis that both the new phases of helium-3 are indeed Cooper phase, Cooper paired, and therefore presumably superfluid phases. Specifically, the A phase could be the ABM phase, and the B phase could be the BW phase. At that particular point in time, the longitudinal resonance had not been seen, but Davosharov quickly, who by that time moved to Bell Labs, quickly set up that experiment, and by a year later, by the summer of 1974, he had indeed observed the longitudinal resonance as predicted in the B phase. And that, I think, was what really clinched it, that people said, okay, now there's really no doubt, this is what we're seeing. Let me briefly conclude with what is superfluid helium-3 good for. Now, here I have to tell a slightly embarrassing story. When I went to the Nobel ceremonies in Stockholm in December of 2003, it turned out that I was not the only person from the University of Illinois who had got a Nobel Prize that year. In fact, my colleague, Paul Lauterbur, from the in fact, he's in the Department of Chemistry at Illinois. He actually received the 2003 prize for physiology and medicine. And the reason he received it, slightly ironically, was that he, in fact, was a pioneer of magnetic resonance imaging, MRI. Now, one of the common features of these Nobel meetings is that you get a lot of press conferences. And so very often I would be standing next to Paul Lauterbur at the press conference. And the journalists would ask Paul Lauterbur, Professor Lauterbur, please explain how your research has been of benefit to mankind. So of course Lauterbur was able to say, well, we've developed these MRI techniques, and by doing so we're able to diagnose dozens of different diseases and so forth, and we've been able to evolve cures, and literally the lives of millions of people have been made more comfortable, and probably tens of thousands of lives have been saved by these techniques. Fine. Then the journalist turned to me and said, and Professor Leggett, please explain how your research on superfluid helium-3 has been of benefit to mankind. At which point I had to look them in the eye and say, well, if you mean in terms of direct, immediate applications, then I have to tell you that superfluid helium-3 is probably the most useless system ever invented by mankind. However, we go a little further. I think there are some things that superfluid helium-3 is good for, slightly more indirectly. First of all, it's the most sophisticated physical system of which we can claim a detailed quantitative understanding. Or at least it was in those days. I think nowadays people might say the fractional quantum Hall effect was more sophisticated, but at least at the time it was the most sophisticated. And there are all sorts of effects of which we can claim detailed quantitative understanding in superfluid helium-3. I have no time to go into those now, but for example, the very interesting questions concerning textures, orientational dynamics, topological singularities, and much of the understanding that we've got from helium-3 has more recently been applied to other systems, like, for example, the high-temperature superconductors, and to some extent even the topological insulators. So from that point of view, I think it has been quite useful. A number of people, particularly Bishop Volvic, have emphasized that helium-3 is in many ways a system with a lot in common with systems in particle physics and cosmology, and so forth. It's very useful for studies of some aspects of turbulence, and we can name another thing, but let me just finish with one specific illustration. The reason I'm going to give this particular example is that I think it does illustrate particularly dramatically the consequences of the fact that Cooper pairs must always behave in exactly the same way. Now we've already seen, in some sense you could say the NMR effect is already a consequence of that, but let's look at a slightly different one. It's believed by particle physicists that the so-called weak interaction has a large component which violates parity, that is, it's not invariant under inversion. This, of course, as you know, is the famous results of Li, Yang, and Wu, but it does not violate time reversal. There is a very tiny bit which violates time reversal, but let's forget about that for present purposes. So basically, the weak interaction is P but not T violating. Moreover, it's believed that apart from the charged currents which are involved in the standard weak interaction decays, there are also so-called neutral currents which would give rise to parity violating forces between elementary particles. The question is, how would one try to see any such effects? Well, suppose we try to look for a P violating but T conserving effect on a single elementary particle. Then we're immediately knocked out of court by the fact that for a single elementary particle, any electric dipole moment, D, must, according to the Wigner-Eckert theorem, must be proportional to J. Now, having a non-zero value of J would violate not just P, but also T. So that's out. However, in the case of the B phase of helium-3, we can actually form a vector, D, which is proportional to L cross S. You remember that was not zero, or it need not be zero. In fact, it turns out it turns out to be along this rotation axis of L, S around L. And the amusing thing about that is that it violates P but not T, so that it would fit into this scheme here. Now, if you just try to work out what the magnitude of the parity violation effect, that is the magnitude of the dipole moment, electric dipole moment, is for a single pair is just undescribably tiny, and many, many orders of magnitude below what can currently be excluded by, for example, neutron scattering, now neutron experiments. However, here comes the crunch. All the Cooper pairs have to behave in the same way, must all have the same value of L cross S. So just as in the case of the nuclear dipole interaction, your effect is multiplied by a factor of the order of 10 to the 23, which jacks it up into a value which is still small, but it is not so small that it might not make some sense to try to look for it experimentally. And indeed, a few years ago, Dolgosharov did start to setting up this experiment. Eventually he found there were just too many interfering factors, and his resolution at the time was just not quite enough to do it. But I think eventually he or someone else is going to get back to this and try to do that experiment. And if it did come off, I think it would be really rather amusing, because it would be our very first example ever of an effect of the weak interaction, and in particular the parity violating aspect of the weak interaction, which is can actually be seen at the macroscopic level. So I believe it would be a fun experiment to do if one can indeed do it. Anyway, I hope I've given you some kind of feeling for the sort of excitement which surrounded these early days of work on superfluid helium-3 in the early 70s, and have some idea of the kind of role I know myself played. Thank you.
Thank you very much. So we have plenty of time for questions.
So, Tony,
would you identify yourself?
my name is Yoshitaka Tanimura from chemistry department here. And so, Tony, so you mentioned about the importance of the dipole-dipole interaction. The dipole-dipole interaction changes a lot as a function of the distance between the atoms. And at the beginning, you showed about the size of the BCX. And so I wonder how it looked like for this case.
So maybe we should just go back to that. Let's see if okay. So yeah. So you're worried about the fact that the actual interaction, the non-dipole interactions, are van der Waals, right? Yeah. Well, so okay. So, well, crudely speaking, what it means is that although the two atoms involved in forming a Cooper pair, they have to be able to approach to this short distance of about 3 angstroms in order to get any attraction at all. Nevertheless, they spend most of their time much further apart, just as is the case with electrons and superconductors, actually. So most of the time, they're not actually feeling much of the dipole-dipole interaction. And so you have to do quite sophisticated calculation to work out the value of this constant, which occurs in the NMR sheet. But a few years after my own work on this, there was a rather nice paper by Fomine, Pethick, and Smith, which did that calculation, and I think did it to a rather good, with a rather good degree of approximation. So, so it can be done, but it's not trivial by any means.
Can I ask another?
Maybe we will return to your second question later. ダイポール相作用は距離によるので、その計算単に10の23乗倍にできるのかということですが、クーパーペア作っている間離れているのも含めて、計算がちゃんとなされているということです。Any other questions, especially students? Tell the students to ask any kind of questions.
Yes, I think there was one. We have one over here. Yeah.
Okay.
Thank you for your lecture. My name is Takuya Nishiyama, the first year of master class of Kyodai physics. My question is, what did you spend the Nobel Prize money on? Please forgive me for asking you a question not connected to physics.
You don't have to answer.
The answer is very simple. I wish I knew. I'm not, it's sort of, well, I'll tell you what happened to about 35% of it, it is now in the US Treasury. Because they took that much in tax. The rest of the other 65%, I'm afraid I have some difficulty accounting.
Thank you.
だから 35% は税金に使われた。Other questions for physics and non-physics? So we go back to the second question, right?
My second question is non-physics question.
Yes.
So if I understand correctly, you are working on this problem to disprove the quantum mechanics.
That was my original hope.
Yeah, and also you are working on the quantum dissipative dynamics because the dissipative system.
Yeah, later I will.
Yeah, but again, you also try to check the foundation of the quantum mechanics. Yeah. And my question is, are you keep working on this direction?
Well, yes, I'm still very interested in designing and analysing experiments which will test how far quantum mechanics remains valid as we push it up from the level of the atom towards the level of our direct experiment. I still think that's a very fascinating question.
But you believe that quantum mechanics, don't you?
As the late John Bell would have said, for all practical purposes, in my everyday work, I believe quantum mechanics is. I'm not prepared to believe that it's necessarily going to be the ultimate truth.
Thank you very much.
Thank you very much. Please. Could you identify yourself?
Yeah, my name is Shinya Oki from YITP. And my question is, in the absence of the external field, what makes the EW state stable, and for the ABM state unstable? What kind of interaction?
Oh, okay. Well, as I say, this is only true within the original BCS theory. And the reason, crudely speaking, is that other things being equal, in order to get the lowest energy, you need to have a gap, an energy gap, which is as isotropic over the Fermi surface as possible. Now, in the case of the equal spin pairing phase, there have to be nodes in your gap, so it can't be completely isotropic. In the case of the Balian-Wertheimer phase, however, it is completely isotropic. So that always wins in BCS theory. And you have to go beyond BCS theory to explain why the ABM phase is ever stable.
Thank you. Any other questions? Identify yourself, just
My name is Kenji Shida. I'm belonging in the physics department. So your idea is showing us very new because that you linked superfluidity with ferromagnetism. So such a new idea, I'm very surprised. Such a new idea come out just after the discovery of the superfluidity. So then my question is that I wonder when such a new idea hit in your mind. So because that I think new idea you had such a new idea before discovering superfluid. Am I correct?
Well, no, I mean, I think it was as a result of trying to think about possible explanations of the experimental data that I hit on this idea. And if you ask when exactly, I don't recall, but I suspect it was when I was lying in bed at night, worrying about this.
So after you saw that experimental data?
Yeah, definitely after I saw the experimental data.
Yeah, thank you.
Yes, this was exactly the question I was going to ask. このアイデアさんのクルーシャルなアイデアにいつ気がついたかということですね、ひらめかれたの。そしたら多分ベッドについて寝る前だという。Rather than just after waking up, before sleeping, you were thinking. Any other questions? Okay.
Thank you for your lecture. My name is Hidenari Tanaka, and I'm 4-year undergraduate student, so I'm not familiar with those topics yet. And I'm always wondering, a lot of readings said that the superconductivity and superfluidity is a kind of Bose-Einstein condensation, and when the Cooper pairs went to behave Bose-Einstein condensation, they went to the base state, and they lose, like, I thought that they will lose the momentum, but the superconductivity and superfluidity behave a really drastic phenomena, and I can relate those two things. And do you have some kind of image about that?
Okay, so your question has to do about the relationship between Bose-Einstein condensation and the idea of Cooper pairs?
Yeah.
With P equals 0, lowest energy state, with, say, dynamical superfluid motion.
Ah, okay,
Right?
good, good. Yeah. Okay, yes, I think one cannot understand one can understand the basic phenomena of superfluidity in terms of Bose-Einstein condensation, but it's not that simple, in fact. That is, one has to work at this somewhat. As a matter of fact, I will be talking, in my talk this afternoon, I will no, I'm sorry, I'm wrong. I do have another talk, but I won't give you. Yeah. Okay. Let me give you I can't answer your question completely without writing down quite a few formulas, so let me not try that. But let me try to give you a very hand-waving idea about how we can understand superconductivity. Let's say, because remember, superconductivity just is superfluidity occurring in a charged system. So if we understand one, we understand the other, basically. So here is here's an argument concerning why the idea of Bose condensation or Cooper pairing is related to the experimental manifestations of superconductivity. Suppose I have a normal metal ring, a ring of just ordinary metal like copper, not superconducting. And suppose I induce a transient EMF around that ring, by, for example, varying the magnetic flux through. Right? So I have this EMF pulse. What's going to happen? What's going to happen is that I start the electrons off, but they very soon, so I'll induce a current initially, but that current will die away very quickly. Now, the time will depend on the geometry of the ring, but it will be pretty small. If I do the same experiment in a superconducting ring, then the current which I've induced will essentially flow back in. So you can think of that as one of the major manifestations of superconductivity. Okay, now how is that related to the idea of Cooper pairing or Bose condensation? Imagine a thought experiment in which I have a forest. Now I do mean a natural forest and not a plantation, so the trees are just arranged at random. I do two experiments. I take a group of school children and I instruct them to run through the forest, but I don't give them any special instructions on all this. What's going to happen? They all start off running in one direction, just as the electrons started off in the same direction. But after a time, one of the children is going to find a tree in his way. He's going to swerve. And since he has no special instructions, he will just keep on running in a new direction. And so after a few minutes, all the children will be running around in random directions. That's the analogy with the normal metal. All the electrons, they'll have collided with impurities or whatever. They'll be moving in random directions. There's nothing to stop them doing. Right? Now, second thought experiment. Imagine that I have a very well-drilled platoon of soldiers, and I send them off marching into the forest. They have strict instructions that as far as possible, they are all to behave in the same way. Right? They're all to keep it steady. So eventually, some soldier is going to find a tree in his way. He's going to dodge it, but he has instructions. He's got to get back in step with the others. So he will drop back into step with the others, and even after a long time, the platoon will still, on average, be marching forward. That's exactly what happens in a superconductor, because the Cooper pairs, it's actually not the single electrons, but the Cooper pairs, they have the instructions, as it were, they have to keep in step. They have to all do the same thing at the same time. So if one Cooper pair, this is very true, but if one Cooper pair is scattered by an impurity, it will recover and drop back into line with the others.
So those interactions are really important.
Well, the interactions which maintain the instruction, as it were, to keep the state, yes, very important. Yes.
Thank you very much.
ごく短く繰り返していただきます。質問は、要するにスーパーペア作ってピークをゼロになるけども、その超流動性っていうのとどういう具合にこう組み合わせたらいいかということですか。じゃあ答えとしては2つなんかあって、森になんか子供たちをとにかく進めて言うと何も指示与えないといろんな方向に行っちゃうけど、兵隊でなるべく同じ方向に進めっていう指令を与えると、まあ月にぶつかってもまた元に単位に戻るということですね。そういうインストラクションがある。Any other questions? You have a question? From our organizers.
Good evening. My name is Mark Polo. I'm first year PhD student. I'm a student of Professor Maino. I'm from Mexico. My question is related to maybe experimental evidence. I know, as I understood, that we have found two phases in helium-3. I don't know, or I'm not sure, if are some studies about these phases in superconductivity. I think that they have done, but we haven't found these phases there. Why do you think that are the main difference, or why we don't have that phases in superconductivity?
Okay, so your question is about the difference between liquid helium-3 and superconducting metals. In the case of helium-3, we found, we believe, two different phases, the A phase and the B phase. In superconducting metals, well, I think the general opinion is that in some cases we have found something which is analogous to the A phase. And I believe, now I could be wrong, it's not something I've been into in great detail, but I believe that it's often believed that some of the heavy fermion systems do show something which is somewhat like the B phase. Now the thing is, of course, you see, you don't really have quite the same symmetries in a metal as you do in helium-3. Helium-3 is invariant under all rotations, whereas the electrons in metals are only invariant under a discrete set of rotations. And moreover, you have a very strong spin-orbital effect in many metals. And therefore, the classification is not quite identical to what it is to helium-3. But I believe that there is a lot of theorists at least have the opinion that one or two of the heavy fermion systems do have a phase which is pretty close to helium-3.
超伝導で A 層みたいなものはあるだろうけど B 層がなぜ難しいかというと重い電子系では、B 層のようなものもあるかもしれない。Any other questions? Any more questions? Excuse me, let me go back to the technical question.
Yes.
And you showed that the omega, the frequency shift, is proportional to the second derivative of the dipole energy with respect to the angle.
Yes.
Could you elaborate on the physical, and also the second derivative is proportional to the dipolar energy itself. Is there any easy way, hand-waving way to understand?
The second point is, I think is a sort of formal way to see that, is simply that you can work out the formal expression for the way in which the dipole energy must change under rotation. And crudely speaking, it's got to be a second-rank tensor, and therefore it's only to be followed as the second derivative. It has to be at least in the same order as the property itself. And now as to your first question, I think that's a little more tricky. But if you think of what an Nmr experiment is trying to do, it's trying to, as it were, tickle the spin of the system away from their original orientation. And so, and since you're doing it's a linear experiment, you would expect that it's going to be that any effect of the dipole force is going to be proportional to the restoring force which tries to put them back to their original orientations. And so that since the force is proportional to the derivative itself, that gives you a second derivative. I don't know if that's
Thank you very much. その NMR の A 層のですね、 ダイポールフィールドが出てくる式についてちょっと物理的な理由を簡単な説明を伺いましたけれども、セカンドオーダーの方なのでっていうことと、それから、力が1回微分で、それのさらに微分でくるので2回微分というご説明でした。Okay, maybe we have one more question. I would like to encourage more students to ask questions.
There are no stupid questions.
It's an excellent opportunity for you to some very casual questions have been asked. So you don't. 日本語でも結構です。そうですね。
噛まなきゃならば、
じゃあ日本語でも結構です。どうでしょう。はい、
My name is Tomoki Yukawa, first year student in master course. What do you think is most important in making great achievement in physics study?
I think a very important ingredient is following your own curiosity. That is, if this is a question which you feel you don't understand, I think it's very important to try to look at it your own way and to try to work out some kind of individual understanding of it. And not to worry too much if people around say, oh, that question's trivial, everyone knows that. I think a very good example of this is Einstein's thinking about the principle of equivalence. You remember that for a good 200 years before Einstein, people had known that essentially all bodies, independently of their shape, their weight, their composition, or whatever, they fall at the same rate in the Earth's gravitational field. No one ever thought to ask why. And I'm sure when Einstein did ask why, a lot of his colleagues said, stupid question, everyone knows that, they just do. And yet he persisted, and of course out of that was born general relativity. So I think it really is very important to try to formulate your own your question. On the other hand, I should just make some caveat. Since presumably most of you are physicists, it's important to ask questions which really are physics and not mathematics. Sometimes people tend to get very tied up with the details of mathematical derivation and so forth. And I mean, if you're going to be a pure mathematician, because you have to, and that's fine, but most physicists are not. And therefore, it is important to try to, in some sense, isolate the physical ingredients of the question as distinct from the mathematical ones, and focus on those.
Thank you.
よろしいですか。大事なこと。他にもう最後いいですか。午後にもレクチャーがありまして、午後は時間の矢というテーマでお話しいただきます。